Okay, so do we have anyone with YouTube connection that someone can check it out how it goes out? Guys with the computers, can you take a look how is my streaming? Is what? Is what? Oh, okay, okay. Yeah, because sometimes what happens is that the picture is a little off from the center, so it becomes too difficult to follow the lecture. That's good. Okay, so we're good to go. Let me just check that that camera is on, so everything's supposed to be fine. All right. So is about to get started. So let's get started. So it's 2:15, and as you notice, the lecture time is different what it used to be. And keep in mind that it's going to change pretty much every single week from this on. Next week is no longer going to be on Tuesday, but it will be on Thursday. And the time will be different too, I believe. So it's changing pretty much every week. So put that in your calendar, otherwise it will be very difficult to follow the lectures. And again, what you need to do in this second period is that you have to follow the lectures every single week, because otherwise you soon will recognize that you're completely off and you have no understanding what the subject matter is about. Okay, so what happens in this period? So I'm planning to deliver 5 lectures. They may be 6 lectures depending on my speed, depending on your activity, depending how much you wanted to discuss with me. But what is in my original schedule is 5 lectures. And today we will get started by looking at one more time about multi-body system dynamics. And by the way, this will be absolutely last time we look at that. So we are not going to revisit that topic any longer once today's lecture is done. Today we're going to look at a little bit of different way that how the equation of motion can be constructed. And now you may wonder, is it necessary to know many different ways that the equation of motion can be constructed? Well, not necessarily, but I still wanted to explain this one method to you because it is actually very handy in many practical applications. And what is this new method? That is a method based on embedded technique. And as the title implies, that is a method where the constraints are substituted inside of the original equation of motion. And it's going to give you a minimum set of differential equations. So it's going to be conceptually very different than the one we learned just prior to midterm exam. Okay, so that's what's going to happen today. And then we're going to leave the multi-body system dynamics, and we're going to open a new topic that is modeling of hydraulics. So I scheduled that there's going to be a total of 2 weeks for hydraulics. I don't think it is enough for us, so probably we need to spend lecture ID 9 in hydraulics and 10 in hydraulics, and a little bit about lecture number 11 as well. And then I really want to devote the full lecture for real-time simulation and gamification technology. Because if this is something like how all these theoretical aspects comes to be practical for you, and try to explain very exactly you can use this theoretical knowledge in different product processes. Because you can use them in a different product processes, not just in a product development, but there is a way to use this in marketing efforts, in service business, and so on and so forth. How that all will happen, that I will tell you in the last lecture of this period, which is going to be the last lecture of the entire course as well. So that will be entitled as a real-time simulation games. A little bit about the game technology as well. All right, so that's about it. And before we proceed, this is again the big picture where I would like to follow in this course. And the big picture is how is a machine constructed? So what are the different disciplines? What are the different components you can find in a machine? An example could be this hydraulic driven crane here. And if you look at the crane, yes, there are components that are called mechanical components. And those are the ones that are in the red box here in the middle. And we know how to model them now using a multi-body system dynamics. But you know that the mechanical structure is not the machine if there is no actuators. So there have to be a means of introducing the motion and forces to a mechanical structure. And those means could be, well, they can be many different ways that you can make it happen. You can use a hydraulics, which is very often used because the power density is very high in the hydraulics. But they could be electric drives, they could be pneumatics, they could be water hydraulics and so on. So it's going to be a wide variety of different options. This course we're going to just look at the one option, and that's hydraulics. And that's going to cover this box here. Shortly, I will explain you how is it the control scheme can be added to your simulation model. And then when I'm explaining about the real-time simulation, that's the way that you can actually account the user in your models. Because real-time simulation models, the operator is a user. So that's giving you a little bit of understanding how that is possible. We're really not going to touch much about the working environment because that varies so much depending on the application. But there are some examples that I'm introducing you in that real-time simulation / gamification lecture. Okay, so that's what's going to happen. So, midterm exam. I got a total of 125 participants, which is a good number. I believe that there is a total of 145 students registered to this course, so 20 students disappeared. Don't know what happened for them, but obviously they did not participate at midterm exam. Average in total was 3.6 out of 5. So 5 is a maximum. So it was a, in my mind, you were scoring really well, really well. And then we got a bunch of students that were scoring 5 out of 5. The exam was constructed such the way that scoring 5 out of 5 was very, very difficult to do. Even minor mistake, minor misinterpretation in one single incident was enough to give you, points, lowering your points such the way that you were scoring 4 out of 5. 5 out of 5 is absolutely outstanding achievement. So what I would like to do is that these are, by the way, the student numbers that were able to score 5 out of 5. So can we give a big hand to these winners? Nice. No more award ceremony than that because, I'm not allowed to, to show any names or anything like that. But if you, within this group, please give you some credit to yourself. Awesome accomplishment. Really awesome accomplishment. Also, if you were scoring, 1 out of 5, that already is a good accomplishment because you have to understand that this subject matter is one of the most difficult topics you can find in a master level courses. So everything from this on will be more or less downhill, except there is a Jussi Sopanen's course about machine dynamics. That's pure pain. But other than that, it's just downhill. It's just, enjoying life. And what will happen in this second period? The subjects are way more easier than they are in the first period. Because we're going to speak about hydraulics. We're going to speak about real components. So we are not speaking about very difficult concepts such like virtual displacement and so on and so forth, but something that are concrete, easy to understand. So hold on, keep on watching the recordings and follow the lectures every single week, and this is going to work out fine. No problems. But also one thing that I would like to kind of get back to you is the grading system. Because I'm a little worried about those ones that were scoring 5 out of 5. Why is that? Because here's a formula that gives you the final grade from this course. And now, if you get 5 from the first midterm exam, and then you're going to get 4 from the next midterm exam, so that's going to be 9. We are dividing that by 2. That's 4.5. but because we're always rounding up, that's a mathematical rule. So we're rounding up, so that's going to be 5 for you. 5 from the written exam part. Now, simulation work, as it is listed here, simulation work can give you 1 additional point. That's not very common, but common scenario is that you get 0, meaning that it will not affect your grade at all. Okay, so let's hypothetically say that simulation work will be worth of 0. Still, it's going to be 5, and then you're doing your weekly homework and in-class quizzes. Both will give you 0.25%. Okay, so here's a 0.25. Here's another 0.25. When you put these together, so it's going to be 0.5, and it will be rounded up again. So 5 plus 0.5 will be 6. 6 out of 5. But that's the time when the student affairs office comes after me and say, Aki, you lost your mind. You know, this is not possible. This is not physically possible anymore. So maximum point is 5 out of 5. So keep that in your mind, because of course I would like you to learn and I would like you to enjoy this course. But same time, unofficially, of course I know that this goes to streams out and it's going to be recording, but same time, unofficially, I would like you to follow the principle that is called minimum energy principle. You know what that is? You know, minimum energy to scoring high. You know, now if you're scoring 6 out of 5, you end up to have 5 out of 5 as your final grade. So you are investing too much energy for this one single course, because there are other courses as well. So keep in mind that the 5 out of 5 is absolute maximum. And that already is a very, very good number. If you're scoring 3 out of 5, that already is very good. So this course is important, but other courses as well, trying to maintain the balance. Such the way that, you know, you're scoring high from these courses and scoring high from other courses as well. There is an exception. An exception is if you wanted to be employed as a summer employee, or you want to do your thesis under my supervision, I mean the one that is financially compensated, or you want to do your doctoral studies under my supervision. Oh, then that's a different story. Then you need to really make the best possible effort in this one particular course, because that's what I'm going to look at whenever you come to my office asking position in my team. Okay? But if you don't want to see me after this course, fine, that's fine too. Then 5 out of 5 makes no sense to do more than that. Clear? Makes sense. Okay, so what are your thoughts regarding the midterm exam? It was a bit difficult, I have to admit it. Sometimes there are tricky things that are trying to make you feel confused. Maybe sometimes we manage to do so. Sometimes we are producing too much information for you, and then you may wonder, like, okay, there's this much information. How is that I can use all this information in order to answer this question? Often you don't. I mean, that there is only a certain amount of information you need in order to solve it. Rest, you don't need to care about it. There was a simple, remember just one example, there was a one simple case about beam-like body. Remember, it was like this. And then there was a particle at the end of the beam-like body that was located here. And then the global coordinate system was located in the origin of this beam-like body. And it was mentioned that this angle here was 45 degrees. You remember that? And the question was where this point is located with respect to global coordinate system. And then there was a body reference coordinate system. But honestly, do you need that information to solve it? You don't. You don't. I mean, that it was obviously visible in a picture, on a figure like that, but you don't need it, because you can solve the problem by using a common sense. Of course, there's a little bit of confusion, because I'm always telling you that you are never ever allowed to take a shortcut. But I also say that you're allowed to use a common sense. Or did I? I did. Okay, that's good. That's good. So then I'm safe. I did not. I did not mention anything about the common sense. Or did I? I said, okay, here's when you need to use your common sense. Because of course you can, you can solve this by using this equation that we are very much familiar with. This equation. And you can set your body reference coordinate system whatever you want. Fine. You can do it this way, but you could just use a trigonometric function, sine and cosine, or a sine and whatever you want, because they both gonna give you the same solution. So it's a length of the beam multiplied by sine theta. It's simple like that. So sometimes, but I understand that sometimes when it comes to your screen, you're thinking, oh, everything like how this was in lecture notes and so on, and it's not enough time. I mean, the 2 hours is not much time, and it's a challenge. Okay, so there was a request hoping me to explain every single question in a midterm exam, like what are the correct answers. I'm not going to do it. And there is a practical reason for that. There's actually 2 reasons for that. The first reason is the fact that there's a question bank. And the question bank is somewhat large, so you may see in some of the questions, but there is more in a question bank. And it will take quite a bit of time to cover all those questions. And it's going to take this lecture and the next lecture a little bit as well. And then there is a practical problem, and that is that if I'm going to release all these correct answers, then we need to redo the question bank for next year. Because otherwise you can contact the first year student next year and saying that if you're going to give me, say, 200 euros, I'm going to allow you to see all these questions and correct answers. So I'm not allowing you to make a business like that. Okay? Happy? Unhappy? Okay. All right, so any thoughts? Was it fair? I mean, the exam, was it fair? I admit that there is a big problem in the exam, and that is related to the fact that it's very black and white. So if you answer incorrectly, you get 0 points, and if you answer correctly, you get full points. And that's something that is a bit of the problem, and you know that we worked with that during the summertime, and it will be available for next year students. That is not just black and white, but if you enter your answer incorrectly, it gives you the warning that is not correct. Think about this again, but this time it's going to reduce the maximum points. That's introduced. That's improvements that I would like to introduce for that. Okay, so but no thoughts, no discussion. Okay, so I'm happy if you're happy. Okay, so now what we're going to do then is that we will make one more final effort. We're going to look at the alternative way to construct the equation of motion. This is not going to be based on Lagrange multipliers. But remember in the couple of weeks back, 3 weeks back, at the time that I explained this concept of Lagrange multipliers, there was this mathematical example where I asked to find an extreme of the function such the way that we obey the constraint. And I introduced that there are 2 alternative ways to make that happen. The one way is that we can add the constraint, the original function, with help of Lagrange multipliers. And that's what we did in the case of augmented formulation. But remember there was an alternative way where we substituted the constraint inside of the original function. And we can follow that procedure in multi-body system dynamics as well. So we're simply looking the ways that the constraint can be substituted inside of the original equation of motion, and that's actually very handy because it produces us a minimum number of differential equations. So previous case, we added the constraints, so we added the number of unknowns. This time we eliminate the number of unknowns such that if there is a system that consists of 1 degree of freedom, regardless what's original amount of generalized coordinates, we can only have 1 differential equation to solve the response. So that's what I'm going to explain to you next. And then we're going to move on to hydraulics. So what's up with you guys today? Is it you don't recognize me any longer, or why is that you don't communicate? Am I looking stronger than usually, or so what's wrong with me? Stronger? No? Yes? Okay, yes. Okay, I like you very much, so I'm gonna take that into account in a final grading. Okay. All right. So embedded technique. So let's get started. Let me explain the whole story. So let me show how it goes. This story makes sense, at least in the beginning. In the end of the story, we are approaching the phase where there is a little bit of involving mathematics. But it's very, very important that here in the beginning you pay your full attention to the concept itself, because this is what I'm expecting you to understand. You know, how this is different than augmented formulas. All right? So everything started from this equation that we obtained from a couple of weeks back again. So this is a equation that you get when you set the virtual work done by externally applied forces to be equal than virtual work done by inertial forces. So what I have here is generalized inertial forces, which is mass multiplied by acceleration, and then quadratic velocity vector. Externally applied forces are expressed with help of this vector here, which is a generalized externally applied forces. So external applied forces, inertial forces, they are set to be equal. And now I said that in general case you cannot set this equation to be equal to 0. And you cannot. And you cannot do that because virtual displacement, which is defined here, is not expressed such the way that is kinematically admissible, kinematically possible. How I know that is not kinematically possible? Because I'm introducing the virtual displacement to all the generalized coordinates and knowing nothing about the constraints. So it's meaning that if I have, for example, the pendulum here, I'm introducing the virtual displacement to global x direction, meaning that it's going to move like this. That's not possible. It's not possible because look what's going to happen to this revolute joint. The revolute joint will break. We cannot do that. So we always have to obey however the constraints set system to be. Okay. So the one way we can actually set this to be equal to 0 is by expressing this virtual displacement such that is kinematically possible. Now what it means? Well, it means that if you have a crankshaft mechanism like the one that is shown here, well, here you can take the piston body and you can move the piston body back and forth. Another remaining 2 bodies will follow according to constraints. They're not following the random way or arbitrary way, but they are following because of the constraints setting them to follow the certain motion pattern. Okay, so if we're able to introduce the virtual displacement such the way that the motion is kinematically possible, kinematically admissible, then, and actually only then, we can set this equation to be equal to 0. And that's, by the way, like I mentioned earlier, that the concept of virtual work is often misused. And here where it is often misused, because by the definition, this equation can be set to be equal to 0 only when this is kinematically possible. General case, this is very, very challenging to define because, you know, if you have, for example, a mechanism like the one that is shown here, how is it you can define the displacement such the way that is kinematically possible, such that other bodies will follow this possible way that the constraints will define? That's going to be a great challenge. And again, we wanted to solve the dynamics by using computer simulation, so there have to be an automated way to set the kinematically admissible displacement. Yes, and there is automated way to make it happen. Again, the example about the kinematically possible displacement is this one here, and kinematically, something that is not kinematically admissible is this example here when the connection rod or crankshaft is actually moving from the revolute zone. You are breaking the constraint, and that's why it's not kinematically possible. So is it clear what is kinematically possible and what is not? So it's like a little bit like this. So would you like me to repeat it, or it's clear? So is it yes, please repeat it, or no, it's clear? Meaning I'm confused. I don't know what to say now. So would you like me to repeat it? No? Okay, so let's continue then. All right, so what's the trick behind? So how is that we can make this happen then? Okay, so the automated trick behind to be able to, again, remember what is an ultimate goal we are aiming here. Ultimate goal is to express the virtual displacement. Oh, what a mess, so let me take this off. Okay, so ultimate goal is to express virtual displacement such the way that is kinematically possible. An automated way, because we cannot do this manually. We could do it in a case of crankshaft mechanism like this, but in a case of mechanism like this one here, it becomes too heavy to do it. So that's why we have to find an automated way to make it happen. Now the automated way is as follows. So we're going to go and take a look at the coordinates that are defining our system. Remember, those coordinates are called tenorized coordinates. Now what we're going to do is that we're going to categorize these coordinates to two different categories. The one that is called dependent coordinates. I will get back to that. What are the dependent coordinates? And then the rest will be called as independent coordinates. Generally speaking, you can do this selection as you want. There are some rules. We will get back to those rules, but let's just, for sake of simplicity this time, let's just say that you can do the selection as you please, as you want. Okay? Only thing that is important here is that the numbers, how many coordinates have to be set to be dependent coordinates? Well, number of dependent coordinates have to be equal than the number of constraints in your system. Let's get back to this crankshaft mechanism, the one that is shown here. So in this case we have 1, 2, 3 moving bodies. In planar case we're going to have 9 generalized coordinates. How many constraints we have in the system? So again, so it's 9 generalized coordinates. How many constraints we have in the system? 8. That's 8. That's 8 because, look at that. So the revolute zone here, revolute zone here, revolute zone here. So that's 2 multiplied by 3 because 3 revolute zones. And then the translational joint, that's going to be 2. So that's a total of 8. All right? So now what I need to do is out of these 9 coordinates, 8 have to go to this first category that is called dependent coordinates. Which ones? You can do the selection as you want. Let's say that, if the full set of coordinates are rx1, rx, ry1, theta1, and so on and so forth, you can select all first 8 of them to be dependent one. The final one, which is actually, maybe not the good choice, but because it's going to be constrained, but let's just select that, from out of the 9, the first angle theta, which is this angle here, that's going to be the only one that is not going to that dependent category. Okay, so 9 goes to dependent categories, and what is left will be independent. So independent coordinates is, let's say, the angle that is showing how this crankshaft is oriented with respect to global coordinate system. Now, same time, you understand that the number of independent coordinates will be equal than the number of degrees of freedom. So the number of this one will be equal than the number of degrees of freedom. So that's the selection that I did. Now, okay, so I have a total of 9 coordinates. 8 out of the 9 goes to dependent one, and 1 is independent. So now what I'm aiming here is that I wanted to create the relation between the independent and all the generalized coordinates. Why I would like to do it? Because if I'm able to do so, then it's possible to express this one displacement such the way that others will follow. So how it goes then? It goes such the way that I will use this coordinate partitioning technique. By the way, so this method is called coordinate partitioning method. So I'm going to go and apply this coordinate partitioning method to my Jacobian matrix. So I'm going to go ahead and take my Jacobian matrix, divide that to two different parts. One that is associated to dependent coordinates and one that is associated to independent coordinates. Again, selection you can do as you want. Let's not discuss about that in details yet. So here is a part that is related to dependent part, and here's a part that is related to independent part. So let me give you an example. So I have here more simple mechanism, which is a pendulum structure. Pendulum that is connected to ground via railroad joint. What's the number of degrees of freedom of this system? That's 1. That is 1. So how many dependent generalized coordinates I can select here? 2. Okay, so vector of generalized coordinates in total can be written like this. Now let's select 2 first one to be dependent. Okay, so corresponding Jacobian matrix will have 2 rows, 3 columns, like this. 3 columns like that. You follow me? Okay. Now what I can do is that I can simply look at the Jacobian matrix and take a piece out of it. And the first piece that I will take out of it is I'm going to change the color. It's going to be this part. Oh, this is not good. This part. This is the one that is associated to dependent generalized coordinates. What is left will be independent. And what is left will be actually a vector, not the matrix, but simply a vector. Okay, so that's what I'm going to do. Why I want to do that? Because once I use this equation here, it is possible to solve dependent coordinates from the equation. And the dependent coordinates can be written as it is shown here, and it actually can be written with help of independent coordinates. So that's a trick that I wanted to do. I wanted to find a relation between independent and dependent generalized coordinates. And actually, what I wanted to do is that I wanted to find a relation between the independent generalized coordinates and all the generalized coordinates. That's really what I would like to do. So, but I'm very close to do it. So I'm very almost there. Don't need much to finalize the thing. Okay, what I have here, what is the mapping here? The mapping is that the dependent part is of Jacobian matrix is inverted and then multiplied by independent part. You follow me? Well, we're going to take a look at an example in a second, so that's when things becomes clear to you. Now, all the generalized coordinates can be written as a dependent and independent. And using the relation that was defined in a previous slide, you can find a relationship between independent generalized coordinates and all the generalized, and all the generalized coordinates like here. So that's exactly what I need. That's what I'm after all the time. And why this is important? Because now it is possible to use this relation here, and substitute it here, this equation, and now you can express the virtual displacement by using independent generalized coordinates only, and others will follow. And why this is important? Well, it is important because then it is possible to introduce the virtual displacement such the way that is kinematically possible. Let me summarize this shortly. Okay, and this is, how you can express the virtual displacement such the way that is kinematically possible. So, again, let me go up here. Let me explain it here. And let me go even up here. So this is where I'm going to get started. So this is a short summary. So my ultimate goal here is to express this virtual displacement such the way that is kinematically possible. And I'm going to do it this in such the way that I'm going to express this virtual displacement by using independent generalized coordinates. And the number of independent generalized coordinates is a number of degrees of freedom. And then I'm going to make it possible to do it this such that other coordinates will follow according to constraints. This will be possible by categorizing my coordinates to dependent and independent coordinates. And again, you can do this selection as you want. And then you're going to go ahead and use this same selection to your Jacobian matrix. And once you do it in your Jacobian matrix, then you can find the relation between the independent and dependent generalized coordinates. And it happens with help of constraints, because Jacobian matrix tells you if you're introducing one motion to one coordinate, how the other coordinates will follow. Okay, makes sense? Now you're using this relation, like it is shown here. You're using this relation in your expression of equation of motion, and now you can set this equation of motion to be equal to 0. And now you have only very few number of differential equations, because look what is here. This is only independent generalized coordinates, nothing else. Make sense? Is it difficult? It is difficult. I can admit that. So again, I was giving you this story that this course is pretty much downhill from this on. So it's just enjoying life and telling how you feel about the weather and so on. So it's going to be simple. But there is this one tiny rock in your way. So this final embedded method. Once we're done with that, then we're going to move on to hydraulics. We are not yet completed with the story, but let me ask if you got the concept, because this is a really essential part of this method. You got it? What is that? Mathematically. Okay. So mathematically, well, physically, it means that if you have this connection rod, if you say that I have, you can select one coordinate. Another coordinates will follow, because there is a 1 degree of freedom in a system. So you can select pretty much whatever coordinate you want. Okay, let me select the Rx that is associated to piston body. And let me move the Rx back and forth here, and let me ask how the others will follow. Well, they will follow this way that I just explained to you. So you go ahead and you break your Jacobian matrix into different places or 2 different categories. And this is the way that you can express how the other coordinates will follow this displacement. Make sense? Okay, so because if I move it like here, if the piston goes here, then these two bodies will follow in a certain way, and this certain way is expressed here. That's how it goes. That's the idea. That's the whole idea behind of this embedded method. Okay? All right, so let's move on. Really, the big difference between this method and augmented formulation, where we introducing the constraint with help of Lagrange multipliers. This is a summary of that. In an embedded technique, we are just looking the one generalized coordinates for the system that consists of 1 degree of freedom. If there would be 2 degrees of freedom, then I need 2 coordinates to solve it. Not more than that. But once I follow this procedure, I don't know what are the reaction forces due to the constraints, because the constraints are substituted inside of my original equation of motion. Alternative way was this method based on Lagrange multipliers. In that case, I'm solving each one of the bodies, and I'm solving the reaction forces because of the constraints. So conceptually, very different. Very, very different. Okay, let me ask you this. So remember this, let me make this easier than that. So if you have double pendulum like this. And if you would follow this Augmented formulation, what would be a number of unknowns in that case? How many unknowns you have to define? Can you solve it? Okay, so let's see. So I have here two bodies. Two bodies needs a total of 6 generalized coordinates. So that's 6. Then how many constraints I have? Here I have 2. Here I have 2. So it's 10. So you were correct. What if I would solve this very same system by using embedded technique? What would be a number of unknowns in that case? 2. Correct. So it's not going to be 10 because then it's going to be same numbers, 6, 4, but minus between. So it's going to be 2. The one needs 10 equations to be solved. Another one needs 2. So there is certain advantages associated with this coordinate partitioning technique. But then you don't know what are the reaction forces due to the constraints because this is an information that is lost in a way. So it's no longer available for us. You got it? Okay, so then what we're going to do, here's a summary. So again, everything started here, the concept of virtual work. And now we're going to express this virtual work, the virtual displacement here such the way that is kinematically possible. And first we're going to use this chain rule of differentiation to find the relation between global coordinates and tenuous coordinates. And then we're going to make one step ahead. We're going to find the relation between independent tenuous coordinates and all the tenuous coordinates. And that relation is the one you can find by using coordinate partitioning technique. Putting all the packages together, this is how the virtual work can be now written. And look at what I have here. I have only independent ones that is left. Others disappears. You got it? It's like, yes, can do. So it's almost like a miracle happens here. So it disappeared. Previous case they were added and now they disappeared because they were substituted inside. That's why they disappeared. Okay? Makes sense? Let's look at the one example and then I'm going to have a break. So this example is, I want to find the static equilibrium. I'm applying this to statics, not dynamics, but just to clarify the concept a bit. And I want to use this mechanism that we looked at in a previous case. And remember, this is what we solved by using a MATLAB. So this is a system that consists of one moving body. So it needs 3 tenuous coordinates and primitive joint here and here. So it's a total of 2 constraint equations that are needed. So if using this substitution technique, I only can get one equation to define the static equilibrium. Nothing more than that, just the one equation. So how it goes, let's take a look. So first, let's look what is a vector of tenuous coordinates. Well, that vector is Rx. Well, now it is a bit unclear way, so it's defined as a R1. But what I mean, of course, is Rx here. Then I have here Ry. Oh, hold on. Ry here, and angle theta. So those are my tenuous coordinates. And now I'm selecting 2 of them to be dependent. Rest will be independent. Now I'm going to simply select the first 2 to be dependent. Rest will be independent, meaning 1 will be independent. Okay? You follow me? Okay, so Rx, Ry will be dependent part, and the theta will be independent. Meaning that if I'm going to introduce the rotation, then Rx and Ry will follow because of the constraints. Not the random way, but because of the constraints. Okay, so Jacobian matrix, I'm not going to explain that in details, but this is how it reads. And look at that. So it consists of 2 rows, 3 columns. So I'm going to select the parts that are associated to dependent tenuous coordinates, which turn out to be very handy selection because it's actually identity matrix that is needed here. Rest will be a vector. Okay? Now I'm defining the relation between independent and then all the generalized coordinates. That happens, that's the way that I will invert it, this dependent part of the Jacobian matrix, and multiply the independent part with the inverted part. Okay? And then I'm going to count all the generalized coordinates with the help of this equation. So this relation goes here, and once I have the relation ready, this is how it reads. Now, once I introduce the virtual displacement to my angle theta, this tells me how the other coordinates will follow this displacement. And those coming because of the constraints. Make sense? Okay? Make sense?
Is it I or one?
This one? You asking that one?
No, the identity matrix.
Oh, yeah, this one. This is a bit confusing because this says identity matrix here, and it is identity matrix in general case, but now we happen to have 1 degree of freedom. So identity matrix turn out to be a scalar component, which is a 1. Nothing else. Got it? Any other questions? Okay, so I'm assuming all good. Can you do this? Okay, thank you. So let's move on. So then what I'm going to do is that I'm going to express my generalized externally applied forces. And now once I express those in such the way that is, when I'm using this constant virtual word, I can find the static equilibrium. Okay? So, externally applied generalized forces, there is only one force that is applying in a system. That is a gravity force that is applying in the center of the body reference coordinate system. Okay, so it's very simple. So I'm gonna use the vector u part that is turned out to be 0, 0 vector. With that help, I'm gonna have my mapping matrix that is very simple. So this reads like shown here. Now when multiplying my external applied forces with that mapping matrix, I end up to have a generalized external applied forces. So that's the one that consists of 3 components, and those components are 0, minus mass multiplied by gravity constant, and 0. Okay. Now my final step is this. So I'm going to use my concept of virtual word to find out the static equilibrium. So there's only one force that is applying in a system, that is a gravity force. So I wanted to find where is the static equilibrium of the system with the information that I have. Okay? So I wanted to use this equation. I want to set this to be equal to 0. And the only way that I can make it happen is that I have to be able to express this first with help of generalized coordinates. And then more importantly, with help of independent generalized coordinates. Good? So we're good? Because I'm always a little bit like unsure, like, are you following me, or are you thinking like, oh my God, when is that we're going to have a break? I can tell you, 2 minutes. Within 2 minutes. So hold on, try to hold on. 2 minutes and then you are good to have a rest. Okay? Okay, so then this goes here. And now this is this critical step, critical step, because this is the way we can express the virtual displacement such the way that is kinematically admissible, kinematically possible. Okay? No further thinking. So I'm gonna keep on substituting things here, and then I'm able, then, and only then, I'm able to set this equation to be equal to 0. Okay, so this is how it goes. So this is all this mathematics that I explained to you. So this is going to be first the generalized externally applied forces, and then with help of that mapping matrix, I can set this to be equal to 0. So this is my generalized external applied forces. This is this part here that is following the kinematics. And once I multiply this kinematics with my forces, I end up to have one equation. From that equation, you can solve the angle theta. When angle theta becomes 0, that's your static equilibrium. It becomes 0 when the theta is 90 degrees or what is this? 90 degrees. How much? 107. 100. So it's 90 plus 200 and 270. Correct. So there are these two configurations are like this. Oh my God, very bad drawing. Like this, or other way around, or flipped over. Those are the two possible places that you can find a static equilibrium. Happy? Okay. Final step, right after break, I'm going to introduce how is that you can introduce this in a dynamics. So there's one more step to take, and then we're good. You have a deal? Are you coming back? You're coming back? That's a promise. Okay, see you within. So what do you say? Can we be relaxed and have a decent break? Like usually, it's supposed to be such that there's a lecture, then 15 minutes break. Usually, never ever follow that. So let's be relaxed and have a 10 minutes break. Okay, so it's good. So then we can leave early. Okay.